Welcome to our ultimate guide on real-time weather satellites. Today we'll explore the most advanced systems that provide us with accurate weather data. I'm Dax Hex, and we're about to embark on a cosmic journey, peering down at our own beautiful, turbulent planet. Think about it. Earth, a dynamic sphere of swirling gases and vast oceans, constantly in motion, constantly changing. For millennia, humanity looked up, wondering about the whims of the weather, often at its mercy. But now we have extended our senses, our vision, far beyond the confines of our atmosphere. We've placed sentinels in the void, sophisticated instruments that gaze unblinkingly at the atmospheric dance below. These aren't just simple cameras looking down. They are marvels of engineering and physics, a testament to our relentless curiosity and our drive to understand the forces that shape our world. From predicting the path of a monstrous hurricane to giving you a heads up about whether to carry an umbrella, these orbital guardians play a crucial role in our daily lives, in our safety, and in our comprehension of the complex climate system of our home planet. We'll delve into how these silent observers, perched thousands of kilometers above us, achieve such remarkable feats of real-time accuracy, transforming our relationship with the weather from one of mere reaction to one of informed anticipation. So, buckle up, because we're going to explore the different types of these orbital titans, from those that keep a fixed stare on one hemisphere to those that sweep across the globe, painting a complete picture of Earth's meteorological tapestry. We'll look at the specific missions, the nations behind them, and the groundbreaking technologies they employ. It's a story of science, of international collaboration, and of our unending quest to know more about the very air we breathe and the skies that shelter us. This is your front row seat to understanding the sentinels of our skies. Let's begin. First up, let's talk about a truly ingenious concept: geostationary satellites. Imagine you want to keep an eye on a specific spot on Earth continuously, without interruption. How would you do it? You'd need your satellite to orbit the Earth at the exact same speed that the Earth itself is rotating. This means that from our perspective down here on the ground, the satellite appears to hang motionless in the sky, a fixed point of observation. It's like having a dedicated celestial photographer for one vast region of our planet, always on duty, always watching. This remarkable feat of orbital mechanics occurs at a very specific altitude, approximately 35,786 kilometers, or about 22,236 miles, directly above the Earth's equator. Why this precise altitude, you ask? Well, it's all about physics, specifically Kepler's laws of planetary motion and Newton's law of universal gravitation. At this height, the satellite's orbital period perfectly matches Earth's rotational period, 1 day. It's a delicate cosmic ballet, where the satellite's forward velocity is perfectly balanced by Earth's gravitational pull, keeping it in this unique Earth-synchronous orbit. The beauty of a geostationary orbit is the continuous stream of imagery it provides. Because the satellite is always looking at the same hemisphere, or a large portion of it, we can receive a near real-time movie of weather patterns unfolding. We can watch storms develop, track their movement, and observe the subtle and not-so-subtle changes in cloud cover, temperature, and moisture over vast geographical areas. This constant vigilance is absolutely critical for short-term weather forecasting, what meteorologists call nowcasting, and for issuing timely warnings for severe weather events like hurricanes, tornadoes, and flash floods. Think about the advantage this gives us. Before these eyes in the sky, we were often caught by surprise. A storm could brew over the ocean, unseen, unmeasured, until it hit land. Now, we see them coming. We can monitor their intensity, their direction, their speed, all thanks to this persistent geostationary gaze. This isn't just about convenience. It's about saving lives, protecting property, and allowing us to make informed decisions in the face of nature's power. The data streams down, painting a dynamic portrait of our atmosphere's ever-shifting moods. The instruments aboard these geostationary sentinels are incredibly sophisticated. They're not just taking simple photographs in visible light like your smartphone camera. They're equipped with advanced imagers and sounders that can detect radiation across various parts of the electromagnetic spectrum: infrared, water vapor channels, and more. This allows them to see things that are invisible to the human eye, like the temperature of cloud tops, which can indicate storm intensity, or the amount of moisture in different layers of the atmosphere. It's a multispectral view that gives us a much deeper understanding. This constant flow of information is fed into complex computer models, helping to refine forecasts and improve our understanding of atmospheric dynamics. The sheer volume of data is immense, a testament to the technological prowess packed into these relatively small spacecraft. And because they are stationary relative to Earth, ground antennas can be pointed at a fixed spot in the sky, simplifying data reception. This makes the whole system more reliable and efficient, ensuring that critical weather information is always available to those who need it most. Consider the implications for global commerce, for agriculture, for aviation. Knowing the weather with high accuracy, hours or even days in advance, has profound economic and societal benefits. A geostationary satellite provides that broad, consistent overview, the big picture of weather systems as they evolve over a significant portion of the planet. It's the first line of defense in our global weather monitoring network, a silent guardian keeping watch from the high frontier. The development and maintenance of these geostationary satellite systems represent a significant investment by nations and international organizations. It's a recognition of the fundamental importance of understanding and predicting weather. The engineering challenges are considerable, launching a satellite to such a precise orbit, ensuring it operates reliably for years in the harsh environment of space and managing the continuous stream of complex data. It's a triumph of human ingenuity. These satellites are like cosmic lighthouses, but instead of guiding ships with light, they guide our understanding of the atmospheric ocean that surrounds us. They provide context, the continuous narrative of weather, allowing us to see not just snapshots, but the entire unfolding story. This continuous view is what makes them indispensable for real-time monitoring of rapidly developing high-impact weather phenomena. So, when you see a satellite loop on the evening news showing a hurricane swirling or a line of thunderstorms marching across the land, you're likely witnessing the product of a geostationary satellite. It's a silent, steadfast observer, tirelessly collecting data, helping us to navigate the complexities of Earth's weather machine. This constant, unwavering gaze is the hallmark of the geostationary orbit, a cornerstone of modern meteorology. Now let's zoom in on a specific family of these geostationary guardians, the GOES-R series, operated by NOAA and NASA in the United States. The R in GOES-R stands for revolutionary, and believe me, that's not an overstatement. These satellites, specifically GOES-16 covering the east, and GOES-18 covering the west, represent a quantum leap in our ability to observe weather over the Western Hemisphere, from the tip of South America all the way up to Alaska, and far out into the Pacific and Atlantic Oceans. What makes them so revolutionary? Well, for starters, speed and detail. The GOES-R series satellites can scan the Earth 5 times faster than their predecessors, with 4 times the spatial resolution and 3 times the number of spectral channels. Think about that! It's like upgrading from an old blurry television to a state-of-the-art high-definition multispectrum viewing system. We can see smaller features, track them more rapidly, and understand their composition and behavior with unprecedented clarity. One of the most groundbreaking instruments on board is the Advanced Baseline Imager, or ABI. This is the primary workhorse, providing those stunning images of clouds, storms, and even smoke from wildfires, or volcanic ash. The ABI can take a full disk image of the Western Hemisphere every 10 minutes, and even provide scans of specific regions like the continental United States every 5 minutes. For areas with severe weather, it can zoom in and provide updates as frequently as every 30 seconds. This rapid refresh rate is a game changer for forecasting fast-developing dangerous weather. But it's not just about pretty pictures. The multiple spectral channels on the ABI allow scientists to derive a wealth of information. They can estimate rainfall rates, identify fog and low clouds, even at night measure land and sea surface temperatures, and detect aerosols like dust and smoke. Each channel is like a different pair of specialized glasses, allowing us to see different characteristics of the atmosphere and the Earth's surface. This rich data set fuels more accurate weather models and provides forecasters with critical information. Then there's the Geostationary Lightning Mapper, GLM, the first instrument of its kind in geostationary orbit. The GLM continuously detects lightning flashes both in cloud and cloud to ground over a vast area. Why is this important? because a sudden increase in lightning activity within a storm often precedes severe weather like tornadoes, hail, or strong winds. The GLM provides a vital new tool for improving lead times for these hazardous events, giving people more time to seek shelter. It's like an early warning system embedded within the storm itself. The GOES-R satellites also carry instruments that monitor space weather. Yes, weather doesn't just happen in our atmosphere, it happens in space too, driven by the sun. Solar flares and coronal mass ejections can send blasts of charged particles towards Earth, potentially disrupting satellites, power grids, and communication systems. The GOES-R spacecraft include a solar ultraviolet imager, SUVI, and space environment sensors that provide crucial data for space weather forecasting, helping to protect our technological infrastructure. It's a holistic view of our environment, from the ground up to the sun. The sheer volume of data these satellites produce is staggering. We're talking terabytes flowing down every day. Processing, distributing, and archiving this information is a monumental task in itself, requiring sophisticated ground systems and high-speed networks. This data doesn't just serve national weather services, it's used by private sector meteorologists, academic researchers, emergency managers, and even the aviation and maritime industries. It's a public good with far-reaching benefits. Consider the impact on hurricane forecasting. With the GOES-R series, we can see the intricate details of a hurricane's structure, the eye wall, the rain bands, with incredible clarity and frequency. Forecasters can better estimate its intensity and track its movement, leading to more accurate warnings and evacuation orders. This improved situational awareness is invaluable when lives are on the line, helping coastal communities prepare for these powerful storms. The difference in observational capability is truly night and day compared to previous generations. The high-frequency updates are particularly crucial for aviation. Pilots need to know about rapidly developing thunderstorms, turbulence, and icing conditions. GOES-R data helps to create more precise aviation weather products, enhancing flight safety and efficiency. Similarly, for marine operations, real-time information about ocean conditions, fog, and storm development is vital. These satellites are unsung heroes for countless industries that depend on accurate weather intelligence. The GOES-R program is a long-term commitment, with several satellites in the series planned to ensure continuous coverage for decades to come. GOES-16, formerly GOES-East, and GOES-18, formerly GOES-West, work in tandem to provide comprehensive coverage of North and South America and the adjacent oceans. This robust system ensures that we have a constant high-quality stream of weather information, safeguarding a massive and diverse population. The level of detail and the speed of information have fundamentally changed how we approach weather prediction in the Western Hemisphere. Chapter 3. Journeying across the globe, let's turn our attention to another critical set of geostationary sentinels: the Himawari 8 and Himawari 9 satellites. Operated by the Japan Meteorological Agency, these advanced spacecraft keep a vigilant watch over East Asia and the Western Pacific, a region frequently impacted by some of the planet's most powerful typhoons and other dynamic weather phenomena. Himawari means sunflower in Japanese, a fitting name for a satellite that constantly faces the Earth, much like a sunflower turns towards the sun. The Himawari 8 and -9 satellites are in many ways technological siblings to the GOES-R series. They boast similar advanced imaging capabilities thanks to their primary instrument, the Advanced Himawari Imager. This instrument also provides high-resolution imagery across multiple spectral bands, allowing for detailed observation of clouds, storm systems, volcanic ash, and even aerosols. The level of detail and the frequency of observation are comparable to what GOES-R provides for the Western Hemisphere, which is a testament to the global push for better weather monitoring. Think about the vast expanse of the Western Pacific Ocean. It's the birthplace of some of the most intense tropical cyclones on Earth, known as typhoons. Before satellites like Himawari, these storms could develop and strengthen far from land-based observations, often making landfall with devastating surprise. Now, with Himawari's constant gaze, meteorologists can track these behemoths from their inception as tiny disturbances to their full fury as mature typhoons, providing crucial warnings to densely populated coastal regions in Japan, China, the Philippines, and Southeast Asia. Similar to the GOES-R's ABI, The AHI on Himawari can perform a full disk scan of its coverage area every 10 minutes. It can also conduct more rapid scans of specific regions, such as Japan, every 2.5 minutes. This rapid refresh capability is vital for monitoring the quick evolution of weather systems, including the development of severe thunderstorms and heavy rainfall events that can lead to flash floods and landslides, which are significant hazards in many parts of this region. The ability to see these changes in near real time is paramount. The multispectral capabilities of the AHI are also incredibly valuable. Beyond just visible light, it captures imagery in numerous infrared and near-infrared channels. This allows for the derivation of a wide array of meteorological products such as cloud top height, sea surface temperature, vegetation health, and the detection of fog and low clouds, even at night. These products are essential inputs for numerical weather prediction models and provide forecasters with a comprehensive understanding of the atmospheric state. It's like having a diagnostic toolkit for the atmosphere. The data from Himawari 8 and -9 are not just used by Japan. They are shared widely with meteorological services across the Asia-Pacific region, and indeed, the world. This international cooperation is a hallmark of modern weather forecasting. Weather, after all, knows no borders. The insights gained from Himawari contribute to a global network of observations, enhancing our collective ability to understand and predict atmospheric behavior on a planetary scale. These satellites are truly international assets. Consider the challenge of monitoring volcanic eruptions in this geologically active region, often called the Ring of Fire. Volcanic ash plumes pose a significant hazard to aviation. Himawari's images can detect and track these ash clouds, providing vital information to air traffic control and airlines to help them reroute flights and ensure passenger safety. The ability to distinguish ash from water or ice clouds using multispectral data is a critical capability that these advanced images provide. The continuity provided by having two operational satellites, Himawari 8 and Himawari 9, ensures a robust and reliable service. If one satellite experiences an issue, the other can maintain coverage, preventing gaps in this critical data stream. This redundancy is crucial for operational meteorology, where a consistent flow of information is non-negotiable. It's about building resilience into our global observation system. The imagery from Himawari satellites often produces breathtaking views of Earth, showcasing the beauty and complexity of our planet's weather systems. From the graceful swirl of a perfectly formed typhoon to the delicate patterns of high-altitude cirrus clouds, these images are not only scientifically valuable but also inspire awe and remind us of the dynamic nature of our world. They are a constant reminder of the forces at play around us. The advanced capabilities of Himawari 8 and -9, much like GOES-R, represent a significant leap forward from previous generations of geostationary satellites in their respective regions. This new era of high-resolution, high-frequency observation is transforming weather forecasting and disaster preparedness across the Western Pacific, a region home to billions of people and critical to the global economy. The Sunflower keeps its watch, providing clarity and foresight. Chapter 4. Now, let's shift our focus to Europe, Africa, and parts of South America, where a new generation of geostationary sentinels is taking to the skies, the Meteosat third generation, or MTG series. Developed and operated by EUMETSAT, the MTG system is designed to deliver a significant upgrade in weather forecasting and climate monitoring capabilities for a vast and diverse geographical area. This is Europe's ambitious step into the next era of meteorological observation. The MTG program is not just one satellite, but a constellation of them comprising two types, MTG-I imager satellites and MTG-S sounder satellites. This dual approach is a key innovation. The MTG-I satellites will carry advanced imagers, much like the GOES-R and Himawari series, providing high-resolution, frequent imagery of the Earth's disk. But the MTG-S satellites will introduce a revolutionary new capability, a hyperspectral infrared sounder. This will provide unprecedented detail on the vertical structure of temperature and humidity in the atmosphere. Let's first consider the MTG-I satellites. They will be equipped with the flexible combined imager, which will scan the full Earth disk every 10 minutes in 16 spectral channels. This is a significant improvement over the previous generation of Meteosat satellites. offering higher spatial resolution and more spectral information. This means meteorologists will be able to see weather phenomena in greater detail and with more precision, from rapidly developing thunderstorms over Europe to dust storms sweeping across the Sahara. A particularly exciting instrument on the MTGI satellites will be the Lightning Imager. Similar in concept to the geostationary lightning mapper on GOES-R, the Lightning Imager will continuously detect lightning flashes over Europe, Africa, and the surrounding waters. This capability is crucial for improving the forecasting of severe storms, as increases in lightning activity often precede dangerous weather conditions. For regions that are data sparse in terms of ground-based lightning detection, this space-based capability is a game-changer. Now let's talk about the MTGS, the sounder satellites. These are truly groundbreaking. They will carry an infrared sounder that will provide hyperspectral data. What does hyperspectral mean? It means the instrument measures infrared radiation in many, very narrow, closely spaced spectral bands. This allows for a much more detailed profiling of atmospheric temperature and moisture at different altitudes. Think of it as creating a three-dimensional map of these crucial weather variables. This is expected to significantly improve the accuracy of numerical weather prediction models. The data from the infrared sounder will give us an unprecedented understanding of atmospheric instability before storms even begin to form. By seeing the detailed vertical structure of the atmosphere, forecasters can identify areas ripe for convection and severe weather development much earlier and with greater confidence. This is a leap towards proactive forecasting, moving beyond just tracking existing storms to better predicting where and when new ones will ignite. It's like having an MRI for the atmosphere. The MTG constellation is designed for longevity and continuity, ensuring that these advanced observations will be available for decades to come. The first MTGI satellite, MTGI-1, was launched in late 2022, and its data is already showcasing the remarkable capabilities of the new flexible combined imager instrument. The full deployment of the MTG system will take several years, but once complete, it will represent one of the most sophisticated Earth observation systems ever launched. The coverage area of MTG is immense, stretching from Scandinavia in the north to South Africa, and from the mid-Atlantic to the Middle East. This vast region encompasses a wide variety of climates and weather patterns, from Arctic conditions to tropical systems and desert environments. The data from MTG will be vital for understanding and forecasting weather across all these diverse landscapes, benefiting hundreds of millions of people. Beyond weather forecasting, the data from MTG will also be invaluable for climate monitoring. The precise and continuous measurements of atmospheric variables, cloud properties, and Earth's radiation budget will contribute to our understanding of long-term climate trends and variability. This is crucial for assessing the impacts of climate change and for developing effective adaptation and mitigation strategies. These satellites are not just looking at tomorrow's weather, but also at the climate of generations to come. The development of the MTG system is a major European collaborative effort involving EUMETSAT, the European Space Agency, and numerous industrial partners across Europe. It underscores the commitment of European nations to advancing Earth observation science and providing essential services to their citizens and the global community. The technological challenges are immense, but the potential benefits for weather forecasting, disaster risk reduction, and climate science are even greater. This is science and engineering working in concert for a better informed world. Chapter 5. So far, we've been gazing from the lofty heights of geostationary orbit where satellites keep a fixed stare. But there's another crucial type of weather satellite that takes a very different, yet equally important approach, the polar orbiting satellite. These workhorses fly much closer to Earth, typically at altitudes between 700 and 900 kilometers. And as their name suggests, they travel in orbits that take them over or near the Earth's poles. Unlike their geostationary cousins that see one hemisphere continuously, polar orbiting satellites sweep across the globe in a series of north-south passes. As the Earth rotates beneath them, these satellites progressively scan different strips of the planet's surface with each orbit. Over the course of a day, they can build up a complete picture of global weather conditions from pole to pole. It's like meticulously mowing a vast lawn stripe by stripe until the entire area is covered. Why this different strategy? Well, their lower altitude allows for incredibly detailed imagery and more precise atmospheric soundings. Being closer means their instruments can resolve smaller features on the ground and in the atmosphere. This high-resolution data is absolutely vital for numerical weather prediction models, the complex computer simulations that provide us with forecasts extending several days into the future. These models need detailed global snapshots of the current state of the atmosphere to make accurate predictions. Think of it this way: geostationary satellites are excellent for continuous monitoring of rapidly evolving weather in a specific region, the nowcasting and short-term forecasting. Polar orbiting satellites, on the other hand, provide the comprehensive global data ingest that underpins the accuracy of longer-range forecasts. They fill in the gaps, especially over the vast oceans and remote polar regions where ground-based observations are sparse or non-existent. They ensure no part of the planet goes unobserved. These satellites carry a sophisticated suite of instruments. Advanced images, similar in principle to those on geostationary platforms, but often with even higher spatial resolution, capture detailed pictures of clouds, ice cover, sea surface temperatures, and land features. Microwave sounders are particularly important as they can see through clouds to measure atmospheric temperature and humidity profiles, which is crucial for understanding the structure of weather systems, even when they're obscured by overcast skies. The polar regions themselves are of immense interest, not just for weather, but for climate science. Polar orbiting satellites are uniquely positioned to monitor changes in sea ice extent, glacier dynamics, and snow cover. These observations are critical for understanding the impacts of climate change, as the poles are often where these changes are most pronounced and rapid. The data from these satellites provides an ongoing health check for some of the Earth's most sensitive environmental indicators. Several major international players operate fleets of polar orbiting weather satellites. The United States, through NOAA, and NASA, has the Joint Polar Satellite System. Europe's EUMETSAT operates the METOP series. China has its Fengyun satellites, and Russia also maintains polar orbiting meteorological capabilities. This global constellation ensures a continuous and robust stream of data, with satellites often crossing the equator at different local times to provide a more complete temporal sampling of the atmosphere. The data from these satellites is not just about temperature, humidity, and clouds. They also measure things like ozone concentrations, atmospheric aerosols like dust, smoke, and pollution, and even soil moisture. This wealth of information paints a holistic picture of the Earth system, allowing scientists to study the complex interactions between the atmosphere, oceans, land surface, and cryosphere. It's Earth system science in action, viewed from above. Because they orbit much closer to Earth, polar orbiting satellites complete an orbit in about 100 minutes, meaning they circle the globe roughly 14 times a day. Each pass over a particular ground station is relatively brief, so a network of receiving antennas around the world is needed to download the vast quantities of data they collect. This data is then processed and disseminated globally, often within hours, to weather forecasting centers worldwide. The accuracy of your 3-day, 5-day, or 7-day weather forecast heavily relies on the initial conditions fed into the computer models, and a huge portion of that critical initial data comes from these polar orbiting sentinels. Without their global coverage and detailed soundings, the skill of medium-range weather forecasts would significantly degrade. They are the unsung heroes, quietly gathering the foundational data that makes modern weather prediction possible. Their contribution is immense, though perhaps less visually immediate to the public than the looping images from geostationary satellites. So, we've journeyed from the steadfast gaze of geostationary sentinels like GOES-R, Himawari, and the new Meteosat 3rd generation, to the globe-sweeping vigilance of polar orbiting satellites. Each type plays a unique and indispensable role in the grand orchestra of Earth observation. The geostationary platforms give us that continuous real-time view, crucial for tracking fast-moving storms and providing immediate warnings. They are our frontline observers, watching specific theaters of atmospheric action with unwavering focus, capturing the drama of weather as it unfolds. Then we have the polar orbiters, meticulously painting a complete global picture, stripe by stripe, providing the detailed atmospheric profiles and comprehensive data needed to fuel the sophisticated numerical weather prediction models that look days into the future. They ensure that no corner of our planet's weather system goes unmonitored, from the tropics to the poles, giving us the foundational knowledge for medium and long-range forecasting. It's this complementary partnership, this intricate dance of different orbits and instrument capabilities that elevates our understanding. By combining data from both geostationary and polar orbiting satellites, meteorologists can provide the most accurate real-time weather information. This synergy allows us to see both the forest and the trees, the broad continental weather patterns, and the fine details within individual storm cells. It's a testament to human ingenuity and our collaborative spirit in tackling a challenge as universal as the weather. Thanks for watching, and stay tuned for more insights into the fascinating world of weather science. Keep looking up and keep questioning.